All right. Hello, everyone. I'm Roshan, and the rest of my team consists of Ang, Eniola, and Ifanis. Today, we'll be talking about our 11785 final project, a self-supervised learning approach to solving the Rubik's Cube. Here's an overview of our work. So let's dive right into the problem statement. How can we algorithmically compute a generalizable solution for the Rubik's Cube? That's the question. We explore a deep learning approach to solve the cube. It's self-supervised, meaning no human labeled data, no domain expertise. Only knowledge required is that there's a single known goal state. It's generalizable to not only the 3x3 Rubik's Cube, and the goal is to shorten the number of moves required to solve the cube. Why does all this matter anyway? It's just a puzzle, right? Solving this puzzle without human expertise can provide insights into solving not only other combinatorial puzzles, but also problems in the real world which use ML. And a pretty cool example is listed here below, linked in the medical domain, which can help save lives. So there's a lot of prior work, but we'll touch upon the most recent work, which we built off of. The most recent approach that inspired our work was done by an independent researcher, Kyo Takano, on the applicability of a self-supervised learning technique using transformer models and graphs. So methods. How did we do all of this? We based our work on Takano's paper, and the main task for this problem is data set generation. What this means is we start with a solved cube. Look here at this picture on the right. We start with the solved cube. We apply some scramble, as you can see here at the top. This gives us this scrambled cube. The scramble is 6 moves. And if I gave this cube to you and I told you the scramble, how would you solve the cube? Intuitively, you would just reverse the scramble to get back to the solved cube. So a 6-move scramble means a 6-move reverse scramble to get to the solution. But we note that the random scramble is far from optimal. This isn't the best way to get back necessarily to the solved cube. Maybe we could do it in 4 moves instead of 6. And that's what we aim to solve. So here's how we represented our cube. We use P to represent the position and R to represent a flipped, twisted, or a flipped or twisted state. And we note that goal states are predictable for n by n cubes. What this means is that we know what the goal is for any cube, regardless of what n is, right? We just want all the pieces to be in the proper positions with no flips or twists. And that's exactly represented here on this slide. So the novel twist that we use in this model is to improve our data set generation iteratively in a truly self-supervised manner. So in the below diagram, we see here, we start with a scrambled state from our training data. We start with the scrambled state. We pass this into our model. And what does our model spit out? It spits out a solution sequence, a sequence of moves to get to the solved cube. So now we ask ourselves, this is where our novel twist comes in. We ask ourselves, the length of the solution that our model spit out, is that less than the length of the scramble? If the answer is yes, then we pass this into our optimal training data bucket. And that in turn goes back into our previous model, causing a feedback loop, which will then go back into the solution sequence. So this refines the new model using the previous model iteratively. And we adapted this to the 2x2 cube successfully. So here we note that the model is based on transformers. So the goal is to learn the underlying probability distribution of cube moves. Given a state, we want to generate the most probable previous move out of a list of 18. And we use a cross entropy loss to minimize the error between these two training distributions, these true probability distributions. Then for inference, we use a BFS approach to go in reverse order and iteratively generate the most probable move at each step. Here's our architecture to touch upon this quickly. We use 2 embedding layers, 4 transformers with multi-head attention, a dense layer, and an 18-dimensional softmax output. And those 2 embedding layers consist of piece and position embeddings, like those of BERT. And transformer models have an additional special token as a buffer to integrate information from other embeddings. So now our results. Adding SSL data iteration allowed us to decrease our solution length, and changing out of the many experiments we did, we saw that changing the number of heads in our transformer model decreased our solution length as well, as we can see here in the difference between these 2 images. On the right, we have more heads and we see a lower solution length on average. And here we can also see that our accuracy starts to taper off in our best model at around 100,000 epochs. So to recap, what's the problem? Solving the Rubik's Cube using SSL. Contributions. We refactor the model to PyTorch and added extensibility. We generalized to more than a 3x3x3 cube. And our novel twist, we gave it a nice name, self-supervised learning with continuous active model pruning. This is our data iteration. And the goal is to use SSL to solve the cube in the fewest moves possible, not just solve it in the fewest moves possible. What's our conclusion? SSL with this pruning technique is just as effective, if not more, in solving the 2x2 as it is the 3x3. And the SSL DNNs can find near optimal solutions for all test cases, even before full convergence. This is the whole point of pruning, not just doing the job, but getting it done faster. So here are some next steps, which you can take a look at. References, and a huge acknowledgement and shout out to Professor Bhiksha Raj for his mentorship and guidance throughout this project. We hope you enjoyed, and thanks for watching.